Hello friend, in previous videos we built this concrete and steel, aluminium and epoxy granite CNC beast. In this video I'll be exploring the epic new possibilities of this machine and some of the wackier ways you can use it. Let's dive in. Well, now I feel silly. I've been working on this tool changer, always intending to have it down here out the way with some kind of cover on it. I even started thinking about the linkages that were going to let it come out of here and pivot vertically like this, so the whole rack could stay nicely in a line and come out something a bit like that. None of that's going to work because the side plate of the spindle would bang into any tools. You can imagine it changing in this tool out. This one's going to snag as it goes sideways, and in fact the only way I can see that this could work is if this was oriented in that direction so the spindle could come on to it from the front. Now I'm wondering whether to put it down there somewhere or just have it as a kind of plug-in rack that I can set right back at the front here. I suppose it could pivot out from this somehow or some crazy complexity like that.
You're right, I did jump in the middle a little bit there. Let's go back and see how those tool holders work. You know there is never the right size spring in the box, which is what makes this technique on the lathe pretty handy. It's just set up to traverse as if it's cutting a thread, and the wire's hand tensioned through the tool holder. Now you can buy one-piece plastic compliant mechanism type versions of this tool holder, but where's the fun in that when you've got obstructive skip hoardings to work through and a big CNC machine to learn how to use?
I haven't used this before. I'm slightly worried about running it at the high RPMs, but we'll see how this chuck does.
This is set to go at 4000 RPM, fast for a long wiggly drill bit, but ridiculously slow for a 24,000 RPM spindle. Will it stall out? I think the more right way of doing this would have been to use a shorter stubby carbide drill, and I've read that with a bit like that, the centre pre-drilling wouldn't actually decrease the chances of deadly drill bit shrapnel. The added rigidity of a short carbide bit apparently wonders loads less, and making contact with the pre-drilled cone shape can tend to pull it sideways versus just a flat surface.
Here we have the evolution of the design. So we're used to thinking of the CNC as being really good for mass producing parts, but I think it's also really good for incremental changes where you do a little tweak on a design, come up with the next one, another little tweak in the geometry, next one, and so on. Once you have your final design, of course, you can churn out a bunch of them. Nice. We'll have to consider this a test rack. I've just mounted it kind of inside the frame of the CNC. I think it would work with the machine grabbing the piece and taking it away. They might be a little bit tightly spaced.
More importantly, we're going to have to figure out where we can put it on the machine where the spindle can access it. Let's rewind a bit.
Soon after the last video on the CNC, Wafer from the spindle manufacturer was in touch with me to say that I'd clamped this in completely the wrong place. It was too low down here where the angular contact bearings are housed. Essentially, he said, please move that up. So that's what we're doing here. Just means I need to take it off, drill some new holes, realign things a bit. Ultimately, I think this whole clamp is going to change completely for something a bit better. I always intended for the clamp to add structure to the Z plate there.
This takes us to the huge weakness of basically all gantry type CNCs with a decent amount of Z travel.
18 kilograms, 20, 30 kilograms.
0.1 millimeters of deflection, not very impressive, but the very weakest part of the CNC. Redoing the test with the indicator higher up, you get a much lower result, even with the same low down leverage. With the Z plate raised up, this drops significantly, even with the same force applied. Here we're getting 0.02 millimeters of deflection. That's probably accumulated from lots of different places, like the linear bearings and the ball screws, not just the structure. We tested it in this direction as well, guessing the deflection would be less, and it was.
That direction and that direction, it deflects slightly more. Near the bottom of the travel, it deflects a lot more than near the top of the travel because it's got quite a lot of travel and the Z plate isn't humongous. I could box this whole spindle in with some kind of box section. Not sure it's really necessary. I might end up doing something crazy like that, I don't know. It deflects less than the mini mill, which is pleasing, but apart from that, I don't really know what it all means.
If you're talking about wood, you don't really need to worry about that previous discussion. Rigidity is still kind of useful. It'll help the bit last longer and give you a cleaner cut. But unless you're going super aggressive, compared with cutting metal, it's not too crucial. And of course, rigidity is not the be-all and end-all anyway. Damping and the tooling you use, and tools stick out especially, all make a massive difference, but that's a whole different story. These 3-inch high softwood chunks that are destined to be part of a curved wooden I-beam can have a really quite aggressive cut and still leave a decent finish. What I'm trying to say is that even though extended Z deflection tests can seem disappointing, it still does a decent job in wood. And for the tougher stuff, there's a nice hack. This is one of our first goes with aluminium, and you can see the hack in action. By setting it up like this in the vise, we've approximately doubled the rigidity of the setup, and that's purely by getting it right up off the bed. Now the spindle mount is almost in line with the lower linear guide bearings, which are in turn almost in line with the bearings on the long axis of the frame. All this conspires to reduce twisting moment forces that would cause chatter and deflection at the tooltip.
But you can see the centre finder or something. There was a bit of misalignment when we flipped it over.
Also, this might need a little pushing on. Oh, that's quite the good fit. Well pleased, that is such a good fit. Mounting thing. I don't know exactly what we're going to do with it. Probably tidy up these drills and make a little drill tidy thing and a camera mount. Something like that.
I should say this doesn't necessarily need to be a big vise. It could just as easily be a chuck like this, scavenged from the lathe and mounted on an old disc brake. Or even something like a cast concrete block with a T-slot table on top could work well. What you see here is an experiment to compare how bean can aluminium machines dry versus with mist coolant. The actual parts are going to be cam action clamps. This is material that's being melted and heat treated, and I've got a whole other video on that, but the machine's much better after heat treating. For the scrap stock we tend to use, it makes it actually possible to cut little slices off with a power hacksaw. Without heat treating, it's just too gummy to be able to do this. Even so, most of my attempts at dry cutting end up with aluminium welded onto the carbide bit like this. Right, we're going to try the same thing, but this time with mist coolant, though ideally we don't want it misting, we kind of want it like fog bustering. The super cheap little mist coolers you can get on Amazon work using the Venturi effect. If you take apart and have a look at the nozzle, it's essentially like a paint gun. Paint guns make a nice fine even mist, but that's not really what we want for cutting metals on the CNC. Just look at all that overspray. This is the huge problem with mist cooling in general. Without an enclosure, it gets on everything and is filtered out of the air by your lungs. What you really want is targeted MQL, or minimum quantity lubrication. This is where only just enough fluid is used to lubricate the cut.
Dribbled on me.
The unit I'm setting up now gets a really bad rep online, but contrary to the way it's designed, we're going to use it this way. We'll be pressurizing the tank so we don't need to rely on the Venturi effect. Hopefully that'll give us a flow of droplets rather than a nasty horrible fog.
So if we add pressure in here, we can get the oil coming out. And the nice thing about this is it's got a little on-off switch. You can use the little pin to lock it on as well as off. It's been outside, it's a bit bird pooey. It should work quite well for our purposes.
I should say that despite this being infuriatingly inconsistent, it does do a great job of keeping the aluminium from welding to the end mill. Here's the high-speed steel end mill after that. The setup for mess containment needs some work at the moment though. Another problem with the Miss Coolant is that the cut finish is so good it exposes all the porosity in the crummy bean can aluminium. A whole new setup. We've made a fog buster a like device. For now it's positioned with a flexible camera tripod type thing. The proof of concept chip shield guard thing that was made from an old plastic veg oil container's been replaced by something a little bit nicer, still from the trash. It does a great job of stopping chips filling the whole workshop. We've ditched the 3-jaw chuck in favour of a big chunk of oak with, I guess, a wooden soft jaw type thing. The old disc brake and chuck setup I noticed was vibrating somewhat. Most of that I think because it didn't span the distance between two of the steel under rails, but was kind of relying on the strength of the MDF spoil board. So this big bit of oak spans that distance. The new fog bustery thing really does give out minimum quantity lubrication type amounts, and the air really does a good job of blasting the chips away. Here's the chips we're getting. Maybe someone out there who can read the chips can tell me what they mean.
Here's the other one with the different setup and the slightly fatter end mill. And I don't know whether it was just a better piece of aluminium or what, but I can't see much porosity. There's a little bit there. Irregularities in the surface are just imperceptible until you open your eyes, of course. But you certainly can't feel them. And even when you're looking, I mean, look at that reflection.
Let's make another one so I can point out some curiosities. First, check out just how hot that workpiece is. That's after just a couple of fairly aggressive facing operations. What's interesting is the milling cutter stays absolutely cool to the touch, whereas go anywhere near the workpiece and I'll burn my hand. In terms of this MQL strategy I've been pursuing, I've no idea if that's normal or whether something's horribly wrong. Apart from that little question in my mind, the setup's all looking really quite good, right? Right? Reflecting on this, I wonder if this is to do with the part getting so hot it's expanding and sort of making room for itself in the jaws for some slop. I guess that's why mechanists don't often have wooden vices, perhaps. Anyway, now I've established my undisputed authority in all things clamping, let's talk about how the cam clamps actually work.
Go, that's nice and firm, so we've rotated that way. If we were to use these in tandem, we could get a much stronger hold by rotating the other one this way so that they're locking in opposite directions. A very strong shove in that direction will tend to rotate this open like so. Of course, that same bug can quickly become a feature if you know for sure that all your cutting force is in this direction, you can have it just as a quick release. So you can put it loosely down, tug it that way to lock it in, take it out. Or the other thing you can do is to combine it with an end stop, as in down the back there, slide your piece of wood all the way down to the end stop if it was longer, lock it in. You know it can't slide that way, so you're good. And if you need extra tightness, you can use the spanner there. The anchoring position of this one's offset by 4mm from the center of the circle. That means it has a total range of 8mm. Now, it's always a compromise between how much force you're going to get from the clamping versus the convenience of having a big range. Luckily, I've got an abundance of odd scraps and wedges and things to make up the distance if, for example, I had this in that hole there. In general, though, cam clamps are good for when you've got a similar size piece and you're going to just have multiples of the same setup.
Whatever I try on this machine seems to lead to like a million things I could improve in the future, but let's go back to when the thing was just starting to move. Take any machine with a certain complexity, even if you bought it from a reputable manufacturer, the chances are good things won't work 100% as you expect. If you happen to have built the machine from the ground up, you can basically guarantee this situation is going to occur. This is what's known as a trochoidal or adaptive toolpath. It's one of the first useful operations the CNC is being asked to do. Hopefully you can see that it's quite a bit more complex than just a straight, simple vector toolpath. It's cutting a circular channel using a whole load of small advancing circular movements. It's way more G-code heavy than a typical straight cutting path would be. It's not really necessary in a soft material like this, but for the CNC builder, this is a pretty damn exciting test.
Oh dear.
Okay, that didn't work, but when I went to tidy it up with a simple bog standard toolpath, that worked just fine. Flipping it over, it was able to cut 2 accurate circles with seemingly no problem. Just for completeness, let's look at where this bit of discarded kitchen is going. It's a barrel-on-barrel adapter, I suppose you could call it. It's going to be a nice improvement to our waste vegetable oil filtering system. We mainly use it to run our van. See the conversion video, by the way, it's horribly underwatched.
It's like it's not even a video or something. Oh shit.
Oh.
While we're on the subject, this tank spanner here for the secondary fuel tank was one of the first tester type projects for the CNC. So you see the problem, it was doing relatively simple toolpaths actually quite well, but there was the horrible itch in the back of my mind knowing that the accuracy was slightly off, and for complicated things it became more and more evident.
Before we go back to the glitch hunt, let me rhapsodise over veg oil a little bit more. We've also been using it in the JCB, the chainsaw, and the chainsaw mill. More on topic though, it's the main ingredient in the CNC's MQL system. The next project on the CNC really highlighted the drifting glitch as I came to know it. On the plus side, it gave me cause to way neaten up the wiring, make the routing nice, make sure it was all shielded, make sure the high frequency power going to the spindle was nicely separated and that cable was as far as possible from all the others in the cable chain. It may not look pretty here, but you should have seen it before. And this is kind of mid-debug. Despite all that, and despite trying numerous software-related fiddle-faddle, the machine is still indulging in this kind of shenanigans. This isn't actually supposed to be an air engrave. Somewhere along the line it's losing its Z0 point, getting above its station as it were.
Here's the bug. I had this running a G-code just in the air, cutting nothing, no strain, all going nicely. It was zeroed to this cross earlier. It predictably goes in this direction into this quadrant and raises up.
So I tried things at this point that in retrospect were a little bit silly, like running it through programs at different places in the machine bed, Unless I'd done something really wrong, I didn't think it was a mechanical hardware issue.
I just unplugged all the other axis, and that's the movement in Y direction. So even with the other axis unplugged, the breakout board's completely unplugged, we're still getting plenty of movement. That's a good 1.5 mil.
Here's where I'm going to spare you the details of taking out the breakout board, running G-code that just went back and forth a gazillion times, hours on forums looking for people with similar problems, until near the end of my tether.
This is the voice of someone who's desperately hoping that this will finally return to the cross when we zero it. Please. It's gone the other side. Well, I can repeatedly and predictably make it lose steps in either direction by changing from active high to active low. Can I have active in the middle?
Well, off the back of that unwelcome discovery, we dived into the AC servo driver settings using a prehistoric program called SmartJog, and found they were set up to accept something very similar to step and direction commands, but not exactly the same. One small change of setting, and this, which might seem like a small thing for you, but my life could continue.
Yes, finally.
After all that, and it was a multi-week glitch hunt, making a stupid little collet holder felt so good.
There we go.